do. Okay. So let me just, what I just introduced to you and forgot to record was that we're doing the marble toss experiment and describing that on page 288, and that we have a sample space of 200 little boxes. We'll toss a marble in, shake the box up. It's classical probability, equally likely can be anywhere. We have these events defined: left half of the box, right half of the box, quarter one, quarter two, quarter three, quarter four. Probability in quarter one is 1/4, and 2 is 1/4, 3 is 1/4, 4 is 1/4. We have a diagonal top, diagonal bottom. Even though this is a straight line, we can think of it as crinkled, so that there's an equal number in the top and the bottom, so it's 1/2 and 1/2. We have the top and the bottom. So we have these different events, and next week we're going to look at the connections between the events. And at the end of the chapter, there's 2 projects or puzzles dealing with conditional probability, and I want to sort of describe those. The first one is the purple probability puzzle. So here's the experiment, okay? You have, or the idea, you have 2 jars, right? And they can each hold, well, let me make sure that I'm getting the number right. It doesn't really matter, but let's get this so there's no okay, there's the birthday problem that we've already talked about. That's a standard one. That's not, so you have some questions there to answer. The purple probability puzzle has to do with conditional probability. Okay, you have 2 jars and a bag of 50 purple. You have 50, that's what I want, 50 purple marbles and 50 red marbles. Now, you can place the numbers, and you're supposed to place the number. Your task is put these marbles into these 2 jars in such a way that the following probability experiment maximizes the chances that the outcome has a purple in it. You draw a purple marble out. So what's the experiment? Okay, one of the jars will be randomly chosen, and then someone will reach in, a blindfolded person will reach in and pull out one of the marbles, and you want it to be maximize the chances that you want to distribute the marbles so you have the highest probability possible of getting a purple marble. And what is that probability? And also, how can you justify your answer with conditional probability? So sort of 3 pieces. One, you choose marbles so that purple probability, the event of you draw a purple marble, when you draw one out, is maximized, is maximum possible. 2, what is the probability of that purple marble being drawn? And 3, justify with conditional probability. Okay, well, we don't know about this yet, and you can well, it's like hard to know what exactly the sample space, right? And what because it's like a 2-step process. First, you randomly choose a jar, and then you then you run the experiment, which someone chooses one jar randomly, and so basically the choice of the jar is classical, and the choice of the marble from jar is classical. So that's the first puzzle. That's the probability puzzle, okay? The second one is the Monty Hall puzzle. Problem or puzzle. Okay, so this was based on a game show. Let me see. The page is 288. To starts this it's the end of the chapter. The two projects at the end of this chapter. So what is the Monty Hall? Well, there's a game show. Well, these are preparations. No, you don't have to turn them in, I think. But the issue is that they are models for what I will ask you on a demonstration. So that you're safe from having to turn them in, but you're not safe from having to do a similar but different problem. So you need to understand what these are, because there will be problems on the next demonstration that deals with probability. I mean, the concept check on probability will just be basic questions, what samples, like the exercises, but the demonstration questions will have ones that are like this. So, okay, so there's a game show. Let me explain the Monty Hall puzzle. There's a Monty Hall, there's a game show. It was, I think, in the 1970s and 80s, and the host's name was Monty Hall. That's why it's called the Monty Hall problem. Okay, so here's the game show. What he would do is he'd have contestants on, and each contestant would be shown like three curtains or boxes or whatever. So there's three, like imagine there's three curtains. And what they're told is that there's a big prize behind one of them. Yes, and you want, yeah, so it's, let me see, um, you're saying it's on page 303 if you're using, oh yeah, the Monty Hall puzzle is on page 303. So let's say this is page 303 on the latest revision. Okay, so the game show is you have three curtains and there's a prize behind one of them. For example, this one might be $1 million. This might be and then joke prize, a bar of soap and a goat, or a sack of flour, something like that. So these are relatively unappealing, and this is more appealing, but you don't know what's behind there. So that Monty Hall asks the contestant which there's like 1, 2, 3. Which curtain? Okay. So they might choose one. They might choose one, or they might choose two, or they might choose three. But then after they've chosen, what happens is Monty Hall opens one of the curtains that they did not choose, that was not chosen. Okay, so for example, let's say that now he's not going to open the $1 million prize. He's going to open, like, for example, if you chose one, he's going to open either the bar of soap or the goat. If you chose the bar of soap, he's going to open the goat. If you choose the goat, he's going to open the bar of soap. Then three, this is the sort of the real question. Do you want to switch? Okay. So at this point, one window is open, one of the joke prizes that you haven't chosen. So it might be that what's left is you have two windows, A and B, and you had chosen, one was chosen, and the question is, do you want to stick with your original or switch to B. Now, the game show runners, for the time it was on, thought that, well, there's only two windows, right? It's behind one of them. If someone walked in off the street and had to choose one, they'd have like a 50-50 chance of guessing the right one because it's only behind one or the other. However, sticking with A or switching. So the question is the probability, does it matter? Is it 1/2, or is there a different probability? So that's one question is this, what's the best? So the questions you have are A, what is best strategy? And B, so not answering it, hopefully, Dipanshu, is what is the best strategy? The second is justify this answer with
I just have a question.
condition. Okay, sure. With
So,
conditional, let me just finish the
okay.
words here. So to justify this condition with conditional probability reasoning. Okay. So so that's is not only knowing the best strategy, is how do you justify that with conditional reasoning? Okay, so Dipanshu, you have a question.
Yeah, my question was that if somebody choose the right one, he's still gonna open the wrong one.
Yeah, like let's say the $1 million was behind window one and you chose window one. He's going to open, say, the bar of soap. Now you
Okay.
don't know, so then you're left. Do you want to stick with one or switch to three? Or let's say you'd chosen three and he opens two and asks you, do you want to switch? Do you want to stick with the goat? Do you want to stick with three? You don't know it's a goat. Or do you want to switch to one? So in the first case, if you had chosen one and he shows you the bar of soap, switching from one to three, you'd be switching from the $1 million to the goat. On the other hand, if you'd chosen the goat first and he shows you the bar of soap, switching would take you from the losing answer to the winning one. So switching can, you might want to stick. Sometimes you might want to. Sometimes you might have chosen right. Sometimes you might have chosen wrong. And so, in hindsight, you're going to see, oh, I should have switched or I should have stuck with one. And so the question is, what's the probability? That is, what's the probability? So the question I want to ask is probability of winning if you switch versus probability of winning if you stick with the same answer. So there's sort of like two strategies, and you want to compare the probability of winning with switching with the probability of winning with sticking with the same one. Okay, that's the problem. Now it turns out that the let me see if I can. Anyway, so these are the two problems, and the goal isn't just to know the answer. I mean, you could probably have someone tell you the answer to figure out, but to understand why this answer is correct and to figure out and what is the probability of winning if you switch, the probability of winning if you stick. So this is with three windows. What happens if I, test your understanding of this by saying, what happens if you have four windows or five windows and the rules are different? After five windows, he opens one of the curtains, but not all of them. Or if you have five curtains and you choose one and he opens three of the curtains and asks you, do you want to switch? What's the probability and how do you justify that? Well, all of these questions are easily answered. Well, maybe not easily answered, but they all are understandably connected to the probability problems that we've had before via the notion of conditional probability. So conditional probability is a probability when you have partial information. Okay. And so in the purple probability thing, you it's a question of analysis, of trying to figure out, how do I set up the problem? So here, the problem could be, well, you understood the case with 2 jars. What if you have 3 jars? Or what if the probability of, maybe you roll a dice to choose the jar, and the dice is loaded. So it's like 1/4 for one and 3/4 for the other, but you don't know that. You know it's loaded, say it's 1/4 and 3/4, but you don't know which one it is. So does it depend on whether the choice is random between the 2 jars? So there's lots of sort of, not just the initial puzzle, but sort of the extensions of it, which you want to understand with conditional probability. Okay, so that's what we'll do next week, is begin to learn about conditional probability and try to do these puzzles. And remember that the last time there is the okay, well, not, I didn't want to do this. How did I get this? I want to get exit full screen mode, right? Okay. So in the text, the first puzzle was the birthday puzzle for the project, right? Well, the birthday program, the question, you have these questions here. For example, what's the smallest value of n for which the probability is greater than 90%, 0.9? Okay, well, what happened? So you might figure out this and have a formula for it and use WX maxima, but then what if I ask you, the question might be, okay, so if we treat Martians or Venetians, those who live on Venus or Mars, where the number of days in the year is different. So they have, like, maybe on Mars, your birthday could be like one of 567 days, or how many ever days are in the Martian year. Well, then you could ask the same question. If you have, like, how many Martians do you need to have the probability be 50% that 2 Martians have the same birthday? Or you could deal with people and ask, what is the probability that 2 people were born in the same month, or born on the same day of the week? And so if you understand how this problem works, you can solve those problems. Solving this problem for the 90% requires that you put a formula into a calculator like WX maxima and calculating the results numerically. And it's going to be better if you understand how to do that in WX maxima. So you want to sort of mess with this to understand it at the level of doing these things here, where you have to calculate it numerically. And the best way to do it is to set up a function like this, the probability, where you put in n here, you want the probability of n and getting out. Okay, so each of these projects is important, and instead of having you turn it in, I want you to sort of ask questions about it, make sure you understand it, so that you can be ready for analogous questions on demonstrations. Okay, so let's see.